A transaction is the atomic unit of work that the DBMS executes. Its life cycle is modeled as a finite state machine with the following states. Active, the transaction has started and is acquiring resources, reading and writing data. Think of a child who has picked up a crayon and is drawing. Partially committed, all write operations have been flushed to the log, and the DBMS has decided that the transaction can be committed, but the final commit record has not yet been made durable. The picture is finished but not yet glued. Committed, a commit record is persisted to durable storage. The transaction's effects become permanent. The picture is now nailed to the wall and cannot be erased. Failed, an error such as constraint violation, deadlock, or power loss forces the transaction to abort. The DBMS marks it as failed. Aborted, the undo phase rolls back any changes made while the transaction was active, restoring the database to the state it had before the transaction began. Start to active to partially committed to either committed or failed to either committed or aborted. Mathematically, let tau be a transaction and sigma of t its state at logical time t. The transition function delta maps a state, and an event such as write, error, or commit to the next state, guaranteeing that at any moment the DBMS can unambiguously determine whether the database must be rolled forward redo or rolled back undo. This deterministic state machine is essential for recovery, concurrency control, and for providing the traffic light metaphor that tells the system when to stop, go, or turn back. Atomicity states that a transaction either fully happens or never happens. DBMSs enforce this with write-ahead logging, which records every logical change before the change is applied to the database pages. Logging protocol. For each update the DBMS writes a log record less than LSN, transaction ID, before, after greater than to the log file. The log sequence number, LSN, imposes a total order on all records. The write-ahead logging rule requires that the log record be flushed to stable storage disk before the corresponding data page is written. Recovery semantics. Undo rollback scans the log backward from the last LSN of an unfinished transaction, applying the before image to each page, effectively restoring the pre-transaction state. Redo roll forward scans forward from the most recent checkpoint LSN, reapplying the after images of all committed transactions, guaranteeing that their effects are visible after a crash. Mathematically, for a transaction T, we define two mutually exclusive outcomes. Commit of T is equivalent to for all log records of T are persisted and commit record persisted. Abort of T is equivalent to there exists a log record of T not persisted or abort record persisted. The recovery function R applied to a database state D after a crash C is R of D equals undo of abort of T 1 through abort of T K composed with redo of commit of T K plus 1 through commit of T N applied to D, where the circle denotes function composition. This formalism guarantees that the post-recovery state is either the exact pre-transaction state or the fully committed state, never a mixed half-applied state. Practical example, a banking transfer T transfers $100 from account A to B. The log contains two records, debit A minus $100 and credit B plus $100. If the system crashes after the debit record is flushed but before the credit, recovery will undo the debit, restoring A's balance because the transaction never committed. If both records and the commit record are on disk, redo will replay both, leaving the balances consistent. Explanation: consistency means that every database state must satisfy a set of integrity constraints defined by the schema. The DBMS enforces these constraints at transaction boundaries. Integrity constraints include domain constraints, for example, salary greater than or equal to 0. Key constraints, primary or unique keys. Referential integrity, foreign keys. User-defined checks, custom predicates. When a transaction T proposes an operation set O, the DBMS computes a state transition function F. F maps S times O to S prime. Where S is the current state and S prime the prospective state, F is designed such that for all S inconsistent, for all O, C of F of S and O equals true implies S prime is also consistent. If C of F of S and O evaluates to false, the DBMS rejects the operation, aborts the transaction, and returns an error to the client. Mathematical illustration. Let C balance of S be the predicate balance greater than or equal to 0. For an operation op equals subtract a $10 applied to state S where balance A equals $5, we compute S prime equals f of S and op goes to balance A prime equals minus $5. See balance of S prime equals false. Therefore, op is rejected and the transaction aborts, leaving the database in the original consistent state. Practical example: in an e-commerce order system, a constraint order total equals sigma line item dot price times line item dot quantity must hold. When a new line item is added, the DBMS recomputes the sum and validates the constraint before committing. If the summation does not match the stored total, perhaps due to a programming error, the transaction is rolled back, preserving consistency. Isolation ensures that concurrently executing transactions appear to run serially. Several classic techniques achieve this. Two-phase locking, abbreviated 2PL. Growing phase, a transaction acquires all locks, shared for reads, exclusive for writes that it needs. Shrinking phase, after the last lock is acquired, it may only release locks. Strict two-phase locking holds all exclusive locks until commit, guaranteeing conflict serializability and recovery-friendly schedules. Lock compatibility matrix. Row and column headings are S and X. Row S, S allowed, X not allowed. Row X, both S and X not allowed. Deadlocks can arise. Detection uses wait for graphs. A cycle indicates a deadlock, prompting abort of a victim transaction. Timestamp ordering, abbreviated TO. Each transaction TI gets a unique timestamp TS of TI at start. For each data item X, the database management system keeps TS_R of X, the largest read timestamp, and TS_W of X, the largest write timestamp. Read rule: if TS of TI is less than TS_W of X, then abort, because an old transaction would read a stale value. Write rule: if TS of TI is less than TS_R of X or TS of TI is less than TS_W of X, then abort. This ensures the serial order corresponds exactly to timestamp order, eliminating cycles in the precedence graph. Serializable schedule construction via conflict graphs. Build a precedence graph G of V and E where V are the transactions, and E are edges from TI to TJ when TI's operation conflicts with and precedes TJ's operation. The schedule is conflict serializable if and only if G is acyclic. A topological sort of G yields the equivalent serial order. Example: transactions T1 and T2. Transaction 1 reads A and writes B. Transaction 2 writes A and reads B. Edges T1 to T2 because W of A occurs after R of A, and T2 to T1 because W of B occurs after R of B, forming a cycle, making the schedule non-serializable. Applying two-phase locking, acquiring locks on A and B before any operation, would block one transaction, breaking the cycle. Durability guarantees that once a transaction commits, its effects survive any subsequent crash. This property relies on three complementary mechanisms. Write-ahead logging, or WAL as described earlier, the commit record and all log entries are flushed to stable storage before the transaction is declared committed. The flush operation is usually performed with fsync or equivalent device-level sync primitives. Checkpointing, periodic creation of a checkpoint record that captures a consistent snapshot of the database pages and the LSN of the last log record included in the snapshot. Procedure: first, flush all dirty buffer pages to disk. Second, write a checkpoint start record containing the current LSN to the log. Third, flush the log. Fourth, write a checkpoint end record. The checkpoint allows recovery to start scanning the log from the checkpoint LSN rather than from the beginning, dramatically reducing restart time. Crash recovery algorithm. After a crash, the database management system performs an analysis phase, identifying the set of transactions that were active at the time of the crash, those without a commit record, and the last checkpoint LSN. Then a redo phase starts at the checkpoint LSN, replaying forward all log records of committed transactions and applying the after images to the database pages. Finally, an undo phase scans backward from the end of the log, undoing any changes of transactions that did not commit, using the before images. Mathematical formulation. Let L be the ordered set of log records L1, L2, up to Ln. Define two functions. R of L equals the redo operation of log record L applying the after image. U of L equals the undo operation of log record L applying the before image. The recovery state drec after a crash is drec equals the intersection over L in L commit of R of L, composed with the intersection over L in L abort of U of L applied to D checkpoint. Here L commit is the set of log records of committed transactions after the checkpoint, and L abort is the set of log records of aborted or in-flight transactions after the checkpoint. Practical example, a retail system processes a purchase transaction that writes to the orders table and updates inventory. After the commit record is flushed, the system may still have dirty pages in memory. If a power loss occurs, the checkpoint taken earlier may not contain these pages, but the log records for the transaction are present. During recovery, the redo phase reapplies the order insert and inventory decrement, guaranteeing that the sale is not lost. Explanation: a schedule is conflict serializable if its execution order is equivalent to some serial schedule. The standard test builds a precedence conflict graph, G equals open parenthesis V comma E close parenthesis colon. V equals set of transactions in the schedule. E contains a directed edge Ti arrow Tj if and only if an operation of Ti conflicts with a later operation of Tj on the same data item. Conflict definition: two operations conflict if they access the same data item and at least one is a write. Write read, read write, write write. Theorem: a schedule S is conflict serializable if and only if G of S is acyclic. Mathematical proof sketch: if G is acyclic, a topological ordering pi of the vertices exists. Executing the transactions in the order pi yields a serial schedule S sub S. By construction, every conflicting edge Ti arrow Tj respects the order in pi, so S and S sub S produce the same final state. They are conflict equivalent. Conversely, if S is conflict equivalent to a serial schedule, the order of transactions in that serial schedule induces a topological order, implying G cannot contain a cycle. Concrete example: T1 writes open parenthesis X close parenthesis and reads open parenthesis Y close parenthesis. T2 reads open parenthesis X close parenthesis and writes open parenthesis Y close parenthesis. Operations in order of execution: Step 1, T1.W open parenthesis X close parenthesis. Step 2, T2.R open parenthesis X close parenthesis leads to conflict write read leads to edge T1 arrow T2. Step 3, T2.W open parenthesis Y close parenthesis. Step 4, T1.R open parenthesis Y close parenthesis leads to conflict write read leads to edge T2 arrow T1. The graph has edges T1 arrow T2 and T2 arrow T1 forming a cycle. Hence the schedule is not conflict serializable. Eliminating the cycle: introduce a lock or delay so that either T2's read of X occurs after T1 commits or T1's read of Y occurs after T2 commits. The resulting graph becomes acyclic and the schedule becomes serializable. Explanation: formalizing ACID with algebraic notation clarifies the exact constraints a DBMS must enforce. Let T be the set of all possible transactions. Let S be the set of all possible database states. Each transaction T in T is a partial function from S to S that may be undefined for abort. C is a subset of S, the set of consistent states defined by a predicate C of S. Atomicity: for all T in T for all S in S. If T of S is defined, then T of S is either S or S prime. No intermediate state Si can be observed by other transactions. Consistency: for all T in T for all S in C. If T of S is defined, then T of S is in C. Isolation: define a schedule sigma as a finite sequence of transaction operations interleaved. Let sigma sub S be a serial schedule, all operations of one transaction before the next. Isolation requires that for all concurrent schedule sigma sub C, there exists a serial schedule sigma sub S such that sigma sub C of S0 equals sigma sub S of S0. Durability: introduce a persistence function persist from S to P, where P is the set of states stored on non-volatile media. For all T in T, for all S in S, if commit of T then persist of T of S is in P, and for all crash persist of T of S is in P. Algebraic composition: if T1, T2 are in T, The composition T2 composed with T1 represents executing T1 then T2. ACID ensures that for any sequence T1 composed with Tn, the resulting state lies in C and is persisted after a commit. Explanation: in production systems, the pure theoretical guarantees of ACID clash with throughput, latency, and cost constraints. Engineers therefore choose trade-offs that balance safety against performance. Technique: ACID impact, performance effect, typical use case. Strict 2PL pessimistic locking guarantees serializability, strong isolation. Increases wait time, possible deadlocks leading to higher latency. Typical use case: banking, inventory systems. Optimistic concurrency control, OCC isolation is checked at commit time, may abort many transactions. Low contention leads to very fast reads and writes. Under high contention, many aborts resulting in wasted work. Typical use case: low conflict web services analytics. Write-ahead logging with group commit. Durability assured, but log writes add input-output. Group commit batches multiple commits, amortizing fsync cost, resulting in higher throughput. Typical use case: online transaction processing workloads with many small transactions. Asynchronous checkpointing reduces recovery window, still durable. Checkpoint thread consumes CPU and input-output, may pause foreground work briefly. Typical use case: large analytical databases. Configurable fsync, for example sync equals off. Weakens durability, possible loss of the last few milliseconds. Improves latency dramatically, 1 to 2 milliseconds versus 5 to 10 milliseconds. Typical use case: logging services, telemetry pipelines. Quantitative example: benchmarks on a modern solid-state drive show the following average commit latencies. Full ACID 2PL plus fsync per commit, 8 milliseconds per transaction. Relaxed durability, fsync every 100 milliseconds, 2 milliseconds per transaction, with a less than or equal to 0.5% chance of losing the last 100 milliseconds of work during a crash. Optimistic concurrency with auto retry, 1.5 milliseconds under 1% conflict rate, 12 milliseconds when conflict rate rises to 30% due to abort retry. Real-world DBMS choices. PostgreSQL in NoDB defaults to strict ACID, fsync on every commit. Users can set synchronous commit equals off to relax durability. MongoDB offers write concern levels, W:1, W:majority, allowing applications to trade durability for latency. Cassandra uses tunable consistency, for example quorum and eventual consistency, sacrificing strict isolation for high write throughput. The key engineering decision is risk tolerance. For a financial system, a lost transaction of $0.01 is unacceptable, so keep full ACID. For a social media feed, seeing a post a few seconds late is tolerable, so relax isolation and durability for higher queries per second.